So this chapter is on sensation and perception. If you think of it, you can imagine that the sensation and perception part of psychology is like the peripheral parts of a computer, the CPU being the brain and the mouse and other attachments putting information into the brain or into the computer. And so we'll go through this. This PowerPoint is to supplement the questions. And the videos were just a way of giving you time away from the PowerPoint to take in some of the material. So the first four definitions on this PowerPoint presentation are on the test. I'm just telling you that. So you should memorize or at least know where these are when you take the test. The first definition is sensation. You'll notice that in each definition, the highlighted words or the italicized words are important because they differ from one definition to the next. So it's the physiological process that occurs peripherally in the body, in the 8 senses, not 5, where receptors convert energy from the environment into impulses in the nervous system. And you know what those are called. They're called action potentials. We spent the last chapter talking about that. The second definition, of course, is what happens in the brain. So sensation is from the bottom up, perceptions from the top down. It's the psychological process that occurs centrally within the brain, and it selects, organizes, and interprets the world. It gives meaning to things. And that allows us to interact with the environment. So those are two really important definitions. Two other ones include threshold. It's a point at which any receptor in all 8 senses, we'll go through them, start responding, but it does so at least 50% of the time. You'll notice there's absolute and relative thresholds. This is the definition you should know. So if you have a hearing test and you are given tones to listen to, if you hear them as many times as you miss them, you're right at threshold. And this applies to all 8 senses, as does the next definition, habituation. The point at which a receptor stops responding, not because the sensation stops, but because the stimulus doesn't change. So if you're looking at a light and someone turns it off, that's not habituation. Habituation happens when you fall asleep with the lights on and get used to that, or when someone's wearing a cologne and you don't smell it after a while. So it happens because the receptor stops responding. Okay, and all these early psychologists that studied sensation and perception were actually psychophysicists like the person you met before, Wilhelm Wundt. So this table is really important because this will be on the test. So, and the reason it's on here is because this is really a summary of all of sensation, starting with the sense on the far left and the part of the brain where it goes to, where perception happens, on the far right. And we'll just go through them. The first two are organized together because they both use wave energy. Vision using electromagnetic waves, audition using sound waves. And when you see this table on the test, you need to use the scientific term in the left column. So instead of, if you put seeing down, you're going to get it marked wrong. It should be vision. Instead of hearing, it should be audition. Gustation, of course, is taste, and olfaction is smell. Those two are grouped together because they use chemical energy. Cutaneous sense, vestibular, proprioception, and kinesthesia, we'll go through those in a minute, are all grouped together because they're involved in movement and they convert mechanical energy. So with vision, the organ is the eye and the receptors are rods and cones. Rods, of course, respond to the low illumination and they help us see black and white and shades of gray. Cones work in high illumination and they help us see colors. If you imagine a circle and that's being your retina at the back of the eye, the cones tend to be in the center and the rods in the peripheral parts. They convert electromagnetic wave energy between 300 and 750 nanometers. That's, I think, one of the study questions. And of course, it goes to the occipital lobe, which of course you already knew. Audition, the organ is the ear, obviously, and the receptor is the basilar membrane. So it responds to sound waves. It's not as simple as it seems, though. So air pressure sound waves travel into the inner ear to the tympanic membrane that make it move, so it starts vibrating. And when that moves, it goes to the three bones in the brain, in the ear, that hammer, anvil, and stirrup. And as that mechanical energy is converted from sound waves to mechanical energy, it pushes the oval window and it makes sound waves inside the cochlea where the basilar membrane is. And of course, the sound waves go to the temporal lobe. Gustation is a sense of taste, and of course, the organ is the tongue, obviously. There are taste buds in humans, about 10,000 taste buds on the tongue, and they respond to at least 4, probably 5 different tastes, including salt, sweet, bitter, sour, and the 5th taste is umami, or a savory taste, and they convert chemical energy. The sense of taste goes to the parietal lobe. If you remember the homunculus, there was an area in there for the tongue and the somatosensory homunculus, and that's where it ends up at. Olfaction, of course, is the sense of smell, and the organ is the nose. The olfactory bulb has somewhere between 3 to 10 million receptors on it. It sounds like a lot, but when you consider a dog can have 500 million, it's pretty small potatoes. It converts chemical energy, so as for both the tongue and the nose, the chemicals hit the receptors to cause action potentials, and olfaction goes to the frontal lobes. Incidentally, the letter behind is also areas that each sense goes to, but you don't need to know those. I'd be happy if you just remembered where it went primarily. The cutaneous sense, of course, is the sense of touch, and it goes to the largest organ in the body, the skin, which is jam-packed with billions of hot, cold, pain, vibration, and light and heavy pressure receptors. And it converts mechanical energy. So when you distort a pain receptor, it sends a signal called an action potential to the parietal lobe. The skin is actually the first sense or first defense in the immune system. And that's why so many people have sensitive skin, because they react, their immune system reacts to agents. Vestibular is a sense of head in space. And of course, the organ is the inner ear, not the outer ear, but the inner ear. And inside the inner ear, next to the cochlea, is the semicircular canals. There's 3 of them, and they're oriented in 3 planes of space. They keep your head level and working properly. Excuse me. They convert mechanical energy as gravity tugs on the otolith organs within the semicircular canals. It sends action potentials to the temporal lobe. Proprioception is your sense of limbs in space. So you have stretch receptors, tendon receptors, ligament receptors, Golgi apparatus in each of the muscles, and they convert mechanical energy from those receptors into action potentials that go to the frontal lobe. And finally is the sense of kinesthesia, or movement sense. It uses the same organs in the muscles, stretch, tendon, Golgi, and ligament receptors, and it converts mechanical energy. This is the sense of knowing how to do something. So as you're sitting there listening and watching, you can imagine hitting a golf ball with a golf club if you've done it before and never get out of the chair. So that's an important sense. And all 3 of those are really critical in movement. So let's just briefly talk about the visual system. You'll get a lot of these in the videos if you watch them. Of course, we talked about electromagnetic wave energy, rods that work in low illumination, cones work in high illumination. Rods are connected to bipolar cells with as many as 10,000 to 1, whereas cones have a 1-to-1 relationship with bipolar cells. So cones are used for visual acuity, whereas rods, in a sense, act like motion detectors. And when the bipolar cells connect to the retinal ganglion cells, the axons become the optic nerve. Visual system is a color-based system. And it happens because of photopigments in the three types of cones. There are red, green, blue, yellow, and black and white receptors that account for what's called trichromatic vision. If you lose one of the cones that doesn't work properly, like the red, green, which is most common, it's called color blindness or dichromatic vision. If you lose two types, it's called monochromatic vision. It's pretty unusual. And even more unusual is losing all color sensation from the pigments, and that's called achromatic vision. Trichromatic theory basically says, as you learned in the video, that what we see, the colors that we see, are basically the relative mixture of the turning on and off of the different cones. And the opponent process theory complements the trichromatic theory, accounting for negative after images, because when you look at one color and you turn away from it, it sort of, in a sense, impels its opponent. If it's red, then green turns on. And taken together, they can pretty much account for most types of color vision. Light adaptation is going from dark conditions to light conditions, like going from a dark theater to outside in the daytime. Dark adaptation is just the opposite, going from a light room to a dark room. And it's the time that it takes for you to adapt to be able to see. These things change as you get older, by the way. They do have retinal implants that replace the retina. They're not very advanced at this point, not nearly as advanced as cochlear implants, which I'll mention in a few minutes, that help people hear. Here's the electromagnetic wave spectrum from 300 to 750 nanometers to see from the far left to the far right. And you'll also see that there are three response curves on the image below, and these correspond to the three types of cones. Images are projected through the lens, the pupil, then the lens. They're inverted, and the fovea is the center where you have the most cones are jam-packed in there. You can see how the eyeball's laid out. Some people have nearsightedness, where the image is because of their optics in their eye is in front of the retina, so use a concave lens to push the image back. Farsightedness is just the opposite, where the image, if it were to be focused, would be behind the retina, so use a convex lens to pull it forward. And then there's some people that have misshapen lenses or misshapen eyeballs that have what's called an astigmatism. You'll notice that the image of the pencil is actually outside of the fovea, so you need to get a lens to pull it back into space, into the right place. Here's the visual pathways. Each right side of each retina projects back to the right hemisphere for the right field of vision, and vice versa with the left hemisphere and the left visual field. So each eye provides half the visual field. And the good news with doing this is that you can see with depth perception, and you still have an entire visual field if one eye doesn't work. So this just shows you some different creatures and their visual systems. So on the far left is a human who has lots of central vision in the dark blue and sacrifices peripheral vision because his eyes are in front of his head. In the middle is a swallow, a small bird that flies around, whipping in and out of tree branches. And of course, they need more peripheral vision to bank and curve, so they sacrifice central vision for peripheral vision. And of course, the one on the far right is woodcock, kind of like a killdeer that we have around here, that literally can see nearly 360 degrees. So they have an adaptation because they're ground-dwelling birds, so they need to be able to see a predator before it sees them. The auditory system actually is, the human ear responds between 20 and 20,000 cycles per second, or hertz. That's one of the study questions. Some animals, like dogs and bats, hear up near 100,000 hertz. Some animals, like elephants, hear below 10 hertz. Bats, because they use high-frequency sound waves, that the sound doesn't travel very far, but they use it for echolocating, like insects. Whales use low-frequency sound waves to echolocate too, but they do it over great distances. One of the things that happens because the eardrum can only vibrate about 1,000 times a second is that the brain actually uses a mechanism to help what's called vibrate up to or to capture up to 20,000 cycles per second. And the evidence for this is that when you get up in those areas at that high a frequency, you mistake pitch for frequency or for volume. So volume is the size of the wave in terms of its top to its bottom, and frequency is how often those sine waves occur. This chart indicates that hearing loss range in decibels. That's one of the study questions. You'll notice that a quiet car is at about 50 decibels. A normal conversation is at about 60. If you're in a subway, it's around 100 decibels. A rock concert, of course, is about 120. You've probably noticed if you've been to one that sometimes you lose your hearing. And at about 130, this is one of the questions on the study sheet, you start losing hearing, especially if it's extended for long periods of time. There's a reason that people on tarmacs at airports wear headphones, because they're at about 150. And the highest recorded recently in recent history is about 180 with the space shuttle launch. The Saturn V rocket that put Apollo astronauts into space was at about 200 decibels. And the loudest estimated sound ever recorded on Earth was when a volcano 800 to 1,000 years ago exploded, and they estimated to be about 300 decibels. Incidentally, the lowest decibel reading is a -8 at a sound lab in Minnesota. And it's so quiet in there that a person can actually hear their heart contracting and beating, the valves closing. So it might be interesting to try something like that. You can see as the sound waves go in the lower part of the picture, the high frequency sound waves, because they're lower energy, fall off first, and the low frequency sound waves go all the way to the end of the uncoiled cochlea. You also notice that there are the anvil, hammer, and stirrup, and the semicircular canals in both pictures. Gustation, of course, is a sense of taste. We already talked about that. Super tasters, one of the study questions is what are they? They're people who have more than the normal amount of taste buds, and they tend to not like spicy foods because of their inordinate number of taste buds. And of course, the kinds of jobs they might have would actually include food and wine tasting or coffee tasting. There's an image of a tongue. You can see how they're distributed around the peripheral parts of the tongue. Olfaction, of course, is a sense of smell. We have about 124 different odors that we can smell. I think that's one of the study questions. And of course, there is a connection between taste and smell. Typically gives us some survival value. Most people don't like to eat foods that smell. One of the questions on the study sheet is what is a pheromone? Well, it's a chemical that most mammals and some other animals secrete. It's used in social communication. So when dogs sniff other dogs, they're detecting pheromones. You've maybe heard the adage that dogs can tell if you're scared. Well, that's what they're smelling. They're smelling pheromones that your skin's secreting. And they're naturally occurring. The olfactory bulb sits at the base of the brain, underneath the frontal lobes. Some people that have brain injuries actually damage their olfactory bulb and get a condition called anosia, where they cannot smell. As I said, humans have somewhere between 3 and 10 million receptors. Dogs, of course, have 100 times more. The cutaneous sense, of course, is your sense of touch. We have somewhere between 20 to 30 pounds of skin. And of course, the receptors are within the first couple of millimeters of the skin surface. You'll see pain receptors, light and heavy pressure, vibration, and of course, even hair, nerves around hair follicles. The vestibular sense is your sense of your head in space. And when you spin your head around, or you spin around on a carnival ride, you get the fluid inside the semicircular canal moving. That's why when it stops, it's so hard to stand up straight, because the fluid continues to move. Anyone who's ever had a case of a middle ear infection, had vertigo, knows how uncomfortable that is. Here's what the semicircular canals look like, right next to the cochlea. Sense of proprioception is, as I mentioned, your position of your limbs in space. Incidentally, all of these senses develop over time. So even if you've ever watched an infant learn how to move its limbs, it's very uncoordinated. Its sense of proprioception, where its limbs are, is very primitive. But once it finds its hand and finds its foot and learns how to move them, they develop a great sense of proprioception and how to do things over and over again. So, and we rely on these things. Perception, of course, is the cognitive part. It's from the top down, not from the bottom up. It involves 3 steps: selecting, organizing, and interpreting stimuli. Some of the criteria we use for selecting a stimulus include the characteristics of the stimulus, like how big it is, its color, its shape, whether it's moving or whether it's novel, like Where's Waldo. Or they could include what we prefer. So if you like the Chicago Cubs, you may prefer Cubby Blue. If you like the White Sox, then you like black and white. Or maybe you like a certain smell, or maybe you like a certain instrument, maybe the cowbell if you liked Blue Oyster Cult. But we select things based on our biases, likes, and dislikes. Organization is the purview of the Gestalt psychologists. Many of them spent their careers coming up with rules. Remember, this was about the turn of the last century, when psychologists were trying to make psychology into a science. And so they focused all their attention on rule making, including size constancy, shape constancy, movement, and depth perception. One of the mottos of the Gestalt psychologists is that the whole, WHOLE, is different than the sum, SUM, of its parts, which means that deconstructing and reconstructing something may actually alter it permanently. It's not the same thing. Then it's not just a collection of parts. There's something about the whole. Here's an example of shape constancy. If you were to be able to look at your retina and just look at the cells responding to the lower images, you'd see a rectangle and a trapezoid. But because we can perceive shape constancy, we still see it as a door. One's a closed door and one's an open door. So we add meaning to it. That's what shape constancy is about. Size constancy means that if something's closer and then further away, the image itself doesn't change in size, even though the image on your retina does. We know an elephant 10 feet away is the same as an elephant 1,000 feet away. It's still the same elephant. Here are some examples of Gestalt principles. So the upper left one with the 2 groups of red figures, that's an example of proximity. So we wouldn't say 4 triangles, 4 squares, 2 stop signs, and 2 dots. We would say 2 groups of red figures. The one next to it on the right is alternating lines of X's and dots. That would be similarity. And the one in the middle would be continuity. You wouldn't say there's a wiener that's been cut in half and put on each end of a box. You would say that there's a hot dog with a box in front of it. Here's some more visual illusions. The most common one is called the Muller-Lyer. It's the second one down. It says Muller-Lyer under it. The horizontal lines are both the same length, even though the ends of the arrows make the upper one look longer. It's a very famous one. I like the Zollner one. The lines going from left to bottom right are actually parallel lines, even though they don't look like it. And this isn't something wrong with your eyes. It's just a matter of interpreting in processing and organizing the stimulus, and that's a cognitive issue. Reversible figures, of course, the famous one is on the bottom, the old lady and the hag, or the young lady. So once you see the old lady, you'll also see the young lady, and then they kind of go back and forth, just like the middle one where there's two faces and a cup or a chalice. Perception, then, on the other hand, is based on interpretation. That's the third step. And this is the whole field of cognitive psychology. And if you want to take a class in cognitive psychology, you'll be focusing a lot on attention. So this is all that I have for this presentation. I will put instructions and the test up on the internet, on the Blackboard program, either tonight or tomorrow. And good luck.